everyone, I'm Jiayuan. Welcome to my channel. In the last video, we were talking about the Dirac equation and the spin and the Weyl representation. So today, let's move on. Let's talk about the Weyl spinors. So our topic today is Weyl spinors. First, let's review what we have from the last video. In the last video, we're talking about the Lorentz group. In Weyl representation, the Lorentz group can be written as d of lambda rotation is e to the I over q theta sigma e I over q theta sigma, and then we can also compute that for the rotation we have, for the boost, we have the matrix representation is E 1 over Q chi sigma E minus 1 over 2 chi sigma, and here is 0, 0, 0, 0. And theta is the rotation parameter, chi is the boost parameter, and sigma is just a Pauling matrix. So what we have is these matrices. So what properties does it have? Is it block diagonal? Yeah, right. So does this remind of you something that you learned in the group theory? Right. If we have this transformation, like psi 1, psi 4 prime equals some block diagonal matrix, psi 1, psi 4. So what does this mean? It means that the Dirac spinor is a reducible representation of Lorentz group because it can be written as some block diagonal matrix. So it is reducible. So what can we conclude then? We can decompose the Dirac spinor into two component Weyl spinors. So Dirac spinor is a 4-component spinor. Let's write it down. Dirac spinor 4 components. Now let's write it as some W plus W minus, and each W here is a 2-component spinor. It is called Weyl spinor. So the W plus minus is just the Weyl spinors. It is 2-component spinor. So what can we have? The Weyl spinors in the Lorentz transformation, it can be written as for W plus minus after rotation, it becomes E I over q theta sigma W plus minus, and W plus minus after boost, it becomes E to the 1 over 2 chi sigma. So it transforms separately. So this is Weyl spinor. And what shall we have? Then we can see that we can decompose the Dirac spinor into 2 Weyl spinors. And in general, how can we project a 4-component scene to 2-component scene? So let's introduce a projection operator. projection operator. Let's call it P plus minus. So for projection in quantum mechanics, it should satisfy some properties. So the projection operators should complete, which means that P plus P minus should be identity. And also, if we project twice for a projection operator like P plus squared, it should still be P plus and also for the minus one. And P plus, P minus, or P minus, P plus, they should be orthogonal. So this is equals 0. So these are the conditions that we need for the projection operators. So what's the projection operator? Let's call it a new name. Maybe call it gamma5. It's just a name right now. But right now I will write something about it. We should respect the Lorentz symmetry, which means that the gamma5 should be a Lorentz scalar. So it should commute with the generators of Lorentz group, which means that gamma5 J mu nu should be 0. So what is gamma5? You may think. Maybe we shall find more properties about it. Maybe gamma5 has some relation between the other gamma mu's, gamma matrices. Now I want to say that the anti-commutator between gamma5 and gamma mu is 0, so that I can satisfy this. You can show this like gamma, this thing, you can write it down as this. Since J mu nu is the commutator of gamma matrices, and we can write it down as this. And for this, we know a relationship. It can be some anti-commutators. Gamma mu, gamma u, gamma 5. And some anti-commutators happens here. Okay, so if this should be 0, so gamma 5 and the gamma matrices and some gamma matrices that we know before, gamma 0, gamma 1, gamma 2, gamma 3, it should be anti-commute. So we conclude that this thing should be 0. Right now we didn't talk about the projections. We just say that gamma 5 may be projections and some properties that gamma 5 should satisfy. And in the next video we will talk about the projectors. Yeah, that's all. Thank you.